Welcome back. This is part 2 of chapter 8, the lithosphere, and we're going to now move on to identifying the three major types of rocks. So again, we learned that there are about 90 or so elements within the Earth's crust. Now, again, 8 of those elements make up about 98.5% of the entire crust. But those 90 or so total elements are going to create about 4,000 or so minerals. And those minerals are going to make up different types of rocks. So there'll be thousands and thousands and thousands of different rocks, different types of rocks. But we have to make sense of those. So we're going to break those down into 3 basic types. And these are based on how the rocks form. So rocks form in 3 different ways. So we say we've got 3 different types of rocks. The first type of rock is referred to as igneous rocks. And these are the rocks that are going to form from the cooling and crystallization or solidification of magma or lava. So basically, we're going to have 2 varieties here. We're going to have intrusive igneous rocks. Those are forming from the cooling, the slow cooling of magma inside the earth. So it's going to take a long time to cool, and that's going to give plenty of time to form large visible crystals. Examples of igneous intrusive rocks are granite. We've already talked about granite a little bit. That's the dominant rock of the continents. It's a felsic igneous intrusive rock. And then diorite and gabbro. We'll see in a few minutes that these are all igneous intrusive rocks that have varying amounts of silica and other compounds within the magma. The second variety is referred to as igneous extrusive, and these rocks are formed on the surface of the earth, not in, but on the surface of the earth, and they're going to cool very, very quickly from the solidification of lava rather than magma, or also from the ash that might fall down after an eruption. So those are igneous rocks, and we'll talk about these in detail in just a second. Our second variety is called sedimentary, and the key word here is sediments. So we've got those sediments like clay, silt, sand, gravel, even boulders that are going to be deposited in those low spots, those sedimentary basins. They're going to pile up on top of each other, and the ones on top will crush the ones below. And as they get crushed, it squeezes the water out, and the clay grains cement those grains together. Sometimes new materials come in and fill in the voids, further cementing those sediments into sedimentary rocks. So the process involves compacting from the weight and cementing the grains together to form a rock. Well, the formation of rock from sediments is referred to as lithification. That means rock making. So sediments can definitely turn into sedimentary rocks with that pressure and cementing or lithification process. So typical rocks, shale, sandstone, limestone, conglomerate, all of those being sedimentary rocks. Our last or third type is referred to as metamorphic rocks. And metamorphic rocks are pre-existing igneous rocks or sedimentary rocks or even metamorphic rocks that were subjected to heat and pressure, not enough to melt them, but enough to have the minerals within the rocks realign themselves. So we often see degrees of banding or foliation where the lighter and darker minerals have realigned within the rock. Examples: gneiss, that's pronounced nice, schist, slate, phyllite, not listed here, quartzite, marble, very typical types of metamorphic rocks, depending on what type of rock it was formed from, and also how much heat and how much pressure was exerted in making that metamorphic rock. So we'll go through these a bit more in detail one by one. So first of all, igneous rocks. These are born of fire, so they will either be rocks that were formed from the solidification of rock from magma or from lava. So forming inside the earth with slow cooling and large crystals, or forming outside or on top of the earth with quick cooling and very small crystals, or maybe no crystals at all. It takes time for crystals to develop. So basically, if this blob of magma solidified below the surface, it would create igneous intrusive rocks like granite. Whereas if the magma made its way out to the surface as an extrusive rock, as lava, which would then cool or crystallize into an extrusive igneous rock like basalt or rhyolite. So again, inside the earth versus outside the earth. Again, lava would form igneous extrusive rocks, and magma would form igneous intrusive rocks if that magma cooled slowly below the surface. This is an interesting diagram because there's a lot to it, but easy to diagnose. The numbers here, 50 all the way through 70 plus, represents how much silica is in a magma. So on this side over here, we've got high amounts of silica, and that's basically silicon and oxygen making up the silica molecule. In this case, pure silica would create a mineral like quartz, very light in color. Low amounts of silica would leave plenty of room in the magma for things like olivine and pyroxene. Remember, those are darker in nature with lots of iron and magnesium, heavier elements. So this is going to yield a magma that had only 50% silica in it, would have almost as much dark color material like magnesium and iron. So basically, magmas that are low in silica will be dark in color, typically. Magma that is rich in silica will yield rocks that are lighter in color. One further note, silica is very sticky and very gooey. And if a silica-rich magma tries to squeeze its way up towards the surface of the earth, it's so sticky and gooey, pressure can build up behind it, and it can become very explosive. Whereas low silica content magmas, rich in olivine and pyroxene, so again, lots of iron, lots of magnesium, they tend to be very hot and very runny, and they don't tend to be very explosive. They tend to create eruptions that would be very fluid, lots of flowing of the magma, not exploding of the magma. So let's take a very low silica content magma, high in iron, high in magnesium content, and have that magma make its way towards the surface of the earth, but it doesn't quite make it. It solidifies within the earth very slowly, creating a igneous intrusive rock known as gabbro. That will tend to be very dark in color compared to other igneous intrusive rocks. And if that same magma did make its way to the surface and erupt out on the surface, it would probably flow out and cool to form an igneous extrusive rock known as basalt. So what's the difference between gabbro and basalt? Same magma chemistry, but gabbro is igneous intrusive, basalt igneous extrusive. Basalt cools very quickly, very little in the way of crystal growth, whereas gabbro would tend to cool very, very slowly and give us lots of crystal growth. Let's go to the other side of that diagram. A magma very rich in silica makes its way towards the surface, squeezes its way through, but doesn't get all the way to the surface, stops its rise, and cools within the crust. It will cool very slowly, yield lots of crystals as it slowly starts to solidify into rock, and it will form granite, an igneous intrusive rock high in silica content. On the other hand, if that same magma did make its way towards the surface with that sticky, gooey, high pressure silica trying to squeeze out through gaps or cracks, pressure builds below, it could have a very explosive eruption yielding rhyolite as a rock once it solidifies. So rhyolite and granite, the same magma chemistry. Granite, though, being igneous intrusive, rhyolite igneous extrusive. Rhyolite would also be very explosive rather than being effusive in its eruption style. What's the difference between rhyolite and basalt? They're both igneous extrusive rocks, but basalt, high in iron and magnesium content, low in silica, whereas rhyolite, low in magnesium and iron content, high in silica content. I think you get the point. So if you look at the intermediaries here, we can go from basalt to andesite to dacite to rhyolite as we increase the silica content for igneous extrusive rocks. For igneous intrusive rocks, gabbro to diorite to granodiorite to granite, again increasing in silica content from left to right for those igneous intrusive rocks. So some typical igneous intrusive rocks here. Granite, lighter in color when compared to gabbro. Lots more iron and magnesium content here. So again, high silica content to low silica content. There should be a one arrow direction here, not two. You'll never see granite form, but you will see granite. So if you go to Yosemite Valley, all of these mountains made out of granite. Well, if the granite formed below the ground, how do we see the granite? Well, it's formed tens of millions of years ago and basically formed below the ground and was then uplifted by earthquakes, and the material above eroded away. Uplift, erode away the material above. Uplift, erode away the material until you expose these granitic massifs here, or monoliths in this case. Igneous extrusive rocks, rhyolite, high silica content, basalt, low silica content. Not many visible crystals here, some tiny crystals visible here, but not very many. Basalt, the most common igneous extrusive rock, usually dark in color, and this comes out from a flow. Now, if we're taking a geology course, we'd learn about the different qualities of these types of volcanic flows, from very smooth ones, which we call pohoihoi, to the ones that look like this. It'd be very hard to walk on. If you walk barefoot, you probably go, ah, ah, ah. In fact, these are called ah style lava flows here. And the most blocky ones of all are referred to as blocky flows. So much information for right now. A couple of interesting igneous extrusive rocks. Pumice is like volcanic foam. So imagine, if you would, a very explosive eruption, lots of gases mixed in with the lava. So imagine, if you would, a can of Coca-Cola, shaken up, heated up, shaken up, heated up, shake it up, heated up, take the top off. Psh, out comes that foam. Well, if you were to solidify that foam right away, if it went into super cold air, that foam would be about half rocky material and half air trapped in between the rocky material itself. And that's how pumice forms. So pumice is basically a rock with trapped gaseous pockets inside. And in fact, if you have enough of those trapped gaseous pockets, the pumice could actually float on your bathtub. And the angular pieces of the bubbles make for like sandpaper, so you can scrape off calluses from your feet using pumice. Now imagine if, instead of having a can of Coke, you had a can of Coke that had already been opened, shaken up, gases come out, shake it up, the gases come out, shake it up, the gases come out. Now you superheat that and throw that up into the air and let it cool very quickly. Well, there's no trapped gases in there. So a magma that had very few gases still trapped in, that comes out as a lava and solidifies very quickly, would form a volcanic glass, which we call obsidian. So no crystals here. Now, if you take obsidian and you hit it with other boulders, or you press just correct this in the right way with a boulder, this will break with a fracture that will create a very sharp edge. And you could nap that into spear tips, arrowheads, cutting edges, etc., before the advent of metals, that was what Native North Americans would utilize for their spear tips and arrow tips and, again, cutting edges. Now, sedimentary rocks is our second form of rock. So sedimentary rocks are formed by sediments that have been weathered and eroded away from some rock mass and then moved downhill, eroded, removed, transported by wind, by air, but mostly by water into a low spot, which we call depositional basin. And here, those sediments will pile up and pile up and pile up and pile up and pile up. So basically, if this goes on for thousands, tens of thousands, hundreds of thousands, millions of years, the fresh stuff being dumped on top would be, of course, dumped on top of the older stuff, which is on top of the older stuff. And this could go on for thousands of feet. So basically, the stuff on the top presses down on the ones below, solidifying those lower layers by compressing them together and also squeezing out the water so that the clay grains would cement this rock together. So we get sediments turning into sedimentary rocks. So sedimentary rocks, most of them, I'm being quite general here because there are other types. What I'm describing is referred to as a clastic sedimentary rock, created from these pieces of rock. These classic sedimentary rocks would always be formed deep down because they are buried by all the overburden of the fresher stuff that came on top of them. So we get sedimentary rocks formed down here. Later they can be uplifted and exposed so we can see those sedimentary rocks. So again, another view of this from an older textbook. These mountains get weathered and eroded, providing the source of the sediment. Those are washed downhill, maybe into a river, and that river empties down into a sedimentary basin, like it could be a riverbed, it could be a lake, it could be the ocean ultimately. And so piles and piles and piles of these layers press down on the ones below, turning these sediments into sedimentary rocks. If this was sand, that would get turned into or lithified into sandstone. If this was clay, it would create claystone or shale. If this was boulders, that would get lithified into conglomerate. So we have different names based on what type of sediment is creating the sedimentary rock. So again, large stuff creates something called conglomerate. This conglomerate is if the sediments are rounded. Breccia is if the sediments were more angular. Sand will create sandstone. Silt, siltstone. Clay, claystone, or shale. Now, to be honest, it's very hard to tell when you're analyzing sediments or rock layers, sedimentary rock layers, if you're dealing with a fine silt or a clay, and therefore, many times, if we have a rock unit made out of silt and clay, we call that a shale. So again, gravel, conglomerate. Sand gets lithified into sandstone. Mud, or in this case, silt with some clay, into siltstone. And more clay, shale. Now, another way of forming sedimentary rocks is even through biological activity, where you might get a coral reef that builds up over time. And basically, a newer coral would form on top of older coral, on top of, so you got the newer stuff going on top. And that would yield a huge, immense amount of coral reef below the living reef. So this stuff gets buried over by the new growth, especially as sea levels are rising. In this diagram over here, you might be able to see that if it wasn't for my photo being there. Now, how do we ever see these reefs, or how do we ever see any kind of sedimentary rocks? If they're all formed at depth, well, sometimes tectonic motions and crustal motions are such that areas of the planet are squeezed together, they break, and what used to be ocean bed gets lifted up. So in fact, even at the top of the Himalayas, we've got pieces of old ocean basin, and in fact, some of the fossils trapped in there too, that have been uplifted to over 25,000 feet above sea level. So old ocean, squeezed and then busted up to create the tops of these mountains. So we can often see evidence of old oceanic materials. So this was a ocean bed here. This is off the coast of New Zealand. In this example, there's a major earthquake, and all this area here got uplifted. So this area used to be underwater, and now it's exposed. So this went on and on and on and on and on. Every few hundred years, a major earthquake occurs. We can see beds that used to be or were formed underwater now being lifted above the water or uplifted and exposed. So all of these sedimentary rock layers here, like the shale, sandstone, shale, those were all formed below the water level and have since been uplifted due to tectonic activity. Now, the number one sedimentary rock in the world is shale. So shale is the most common sedimentary rock, and that shows that all these mountains and continents get worn down to the tiniest of pieces, clay and silt-sized grains or fragments before they're ultimately deposited and buried and then lithified back into sedimentary rocks. The second most common is sandstone. The third, limestone. Now, limestone is made up of largely marine organisms, calcium carbonate making up those shells. And then we've got conglomerate and other sedimentary rocks, a very tiny fraction. So if I were to ask you what's the most common sedimentary rock in the world, your answer probably should be shale. This is just showing you what happens when you've got grains that are compacted and cemented together to turn sediments into sedimentary rocks. Here's some limestone that was formed below water and then lifted up or uplifted and exposed, and we now see those outcrops. The same with this sandstone, now uplifted, and some shale from Canada. So basically, when you see these sedimentary rocks, keep in mind they were formed in these horizontal layers for the most part and later uplifted so we can see the evidence of old seabeds and lake beds, etc. Our last type of rock, metamorphic rocks. Metamorphic means they change their shape. So if you imagine that there were some horizontal layers of rock, doesn't matter which kind they were at this point, they used to run across here, but now a mass of magma or a plume of magma made its way up from below and is making its way to the surface. Maybe this magma doesn't go any further than this and it starts to cool off. This would then turn into igneous intrusive rocks. But because of the baking effect and the pressure of that magma coming up, the rocks that used to be part of this layer here, in this zone, they have changed their form. They've been pressurized. They were heated up. They didn't quite melt. They were heated up so they could change their form. And we often see then the lighter and darker minerals align themselves. This is one form of metamorphism called contact metamorphism. Then we have a second form called regional metamorphism, where rocks and slices of our crust are thrust together, and that heat and pressure from that thrusting together is enough to change their form. So these rocks right here, they have changed their form based on the addition of heat and pressure. So these could have been sedimentary rocks before, they could have been metamorphic rocks, they could have been igneous rocks, but they've definitely undergone some transformation, usually making them a bit tougher. Depending on how much heat and how much pressure will tell you what kind of metamorphic rock you have. From shale to slate, phyllite, schist, and gneiss. Gneiss is the metamorphic rock with the highest degree of heat and pressure, where shale would be the lowest. So if we look at shale, remember shale would be a sedimentary rock, but if we start to have that shale subjected to heat and pressure, that shale would turn into a slate. More heat and pressure into a phyllite. More into a schist. And finally, it could turn into gneiss. So again, this is high-grade metamorphism. This would be low-grade metamorphism. And depending on what type of rock you started off with, would also tell you what you're going to end up with. So if you already had a tough rock like granite, granite could be turned into a gneiss, but granite could not be turned into a slate or a shale because it's already a pretty much pressurized crystalline rock to start with. Granite, speckled in color. Remember, that's a felsic rock, lots of silica with other minerals in there. Subject that to high grade metamorphism, it's going to turn it into gneiss with this foliation of the lighter and darker minerals lining up now. Rather than being speckled, they all get lined up in these lines of banding or foliation. Limestone, those calcium carbonate shells. Limestone sedimentary rock, if we add a heat and pressure to that, that will toughen that up into marble. So marble countertops are not going to let the water through quite like limestone would do if you had a countertop made out of limestone. This is too soft. This one is turned into a hard metamorphic rock. So all marble was once limestone. Now, one rock type can become another rock type given enough time. I'm talking geologic time, millions of years. So let's start off with some magma. Magma, molten rock below the surface. And that could stay underground as magma within a plume for millions of years. Or that magma could make its way towards the surface of the earth through the crust and stop. And it will solidify within the crust and form an igneous, intrusive rock like granite. And that granite could then later be uplifted to the surface. That same magma could in fact make its way and burn a hole through the crust and finally come out from magma and then flow as lava on the surface and solidify as an igneous extrusive rock like basalt. That basalt rock is now subjected to weathering, the breaking up of rock, erosion, the removal of that loose rock, and creates sediments, little pieces of rock that will move downhill to a depositional basin, usually by water washing in that direction, and piling up as sediments. The same could be said with those igneous intrusive rocks that were uplifted to the surface, subjected to weathering and erosion, and basically forming sediments that get deposited into that sedimentary basin. Those sediments will pile up over time. And the weight of the sediments at the top pushing down on the bottom, plus a cementing effect, the clay grains, will turn those sediments into sedimentary rocks below the surface. So those sedimentary rocks could be sandstone if the sediments were sand. It could be shale if those sediments were clay or even silt size. It could be conglomerate if those sediments were cobbles. And those sedimentary rocks could stay below the ground for millions and millions of years. Or tectonic forces could change, and now those sedimentary rocks could be uplifted back to the surface, subjected to weathering and erosion, and turned back into sediments. Or those sedimentary rocks formed below the surface could be thrust down deeper and deeper and deeper into the earth, adding more heat and pressure, turning them into metamorphic rocks. So the sandstone turns into something called quartzite. The limestone turns into marble through metamorphism. The shale turns into slate or phyllite. So we form some metamorphic rocks, and they can stay underground for hundreds of millions of years, or they could get uplifted to the surface, exposed to the elements, weathering and erosion, and turning them back into sediments. Or those metamorphic rocks could be subjected to even more heat and pressure, finally melting them and turning them back into magma, where we started. And by the way, those igneous intrusive rocks that we initially had uplifted, those could be exposed to more heat and pressure, turning them into metamorphic rocks. So the granite, rather than being uplifted, could be metamorphosed into gneiss. So given enough time, every type of rock can become another type of rock. Again, it just takes millions, tens of millions, hundreds of millions or more years to complete these elements of the cycle, referred to as the rock cycle. Well, we've got an awful lot of time. Geologic time, 4.6 or so billion years. We break that down into eras, periods, epochs. And in fact, I've uploaded a video for you, which is just a few minutes long, explaining how this geologic timescale came to be. The most important thing I want you to know right now, like in the beginning of the class, the age of the Earth, how long we've been around. And then I'm going to ask you a little bit of information about these various eras, periods, and epochs. Getting towards the end of the chapter here, I just want to introduce a couple of concepts. One of those, the concept of external and internal processes, or internal and external geomorphic processes. If you would imagine, we can look at the Earth and the landscapes of the Earth based upon whether internal or external processes are dominating in an area. Well, internal processes get their energy from inside the Earth. So that's basically volcanoes, the broad warping or bending of the Earth's crust, and the rearranging of the Earth's crust as these tectonic plates, those lithospheric plates, are moving past one another, away from one another, into one another, and making the crust get all ruffled up. So internal processes tend to make mountains higher, valleys lower. So internal processes tend to ruffle up the surface of the Earth. External processes, weathering, that means a breaking up of rock. Several ways that can happen, we'll discuss more. Mass wasting means gravity pulling rock material down from high spots to low spots, like landslides and rock falls. And erosion is the removal of the weathered material and its transportation from a high spot to a low spot, usually by water, but also by wind and ice, like in glaciers. What these tend to do, weathering, mass wasting, and erosion, these external processes, they tend to make high spots become lower. So making a mountain broken down or making it lower. But also that material that's just being weathered and eroded goes towards low spots. So from high spots to low spots. So external processes tend to make mountains lower and valleys fill up, tending to smooth out the surface of the Earth. So if we see a natural environment, we can usually see that if we have a jagged mountain chain, internal processes are probably dominating. If we see a very smooth area, that means that external processes are tending to dominate in that area. Let's look at examples here. So this is in Patagonia, taken from high altitude. This jagged mountain chain is telling us that some kind of internal processes is dominating here, and that's creating a very jagged landscape. So there's probably all kinds of earthquake activity and tectonic forces in motion here. On the other hand, if we look at Bangladesh and the mouth of the Ganges here, this entire area is pretty flat. And that tells us that external processes are dominating in this area. In fact, this is the Himalayas in the background here. So here we see internal processes dominating, and over here, external processes dominating. If we look at a map of the world, we can probably see from here that the yellows and pinks of this are showing areas where external processes are dominating. So these pink zones here. And think about the US as a whole. In the US, not much going on over here in terms of mountain building. But look at the West Coast over here. Internal processes definitely dominating. Same along the coast of South America. So just by looking at this, we can get a very good feel for internal versus external processes dominating in a specific region. All right, so we're moving on, end of this chapter, into chapter 9, our last chapter, where we're going to look at more in detail at plate tectonics and landforms associated with internal and external processes, but dominating our conversation will be the internal processes. Done with chapter 8. In class, we'll have time for questions. We'll see you there.